Hi, my name is Klaus and I'm a PhD student at KTH Royal Institute of Technology, and I'm here to present AquaLang, a streaming data flow programming language. So what is data flow programming? It is a programming model where you formulate your application as a data flow graph that continuously processes incoming data. And the prospect of this model is that as long as you can express your application as a data flow graph, an underlying system can take care of the complexity of how you run this graph by, for example, managing fault tolerance and scalability. Today, there are various systems for running data flow graphs, and these systems provide data flow libraries for building graphs and higher-level query languages for declaratively querying streaming data. So why do we need a new language? Well, let me give you a motivating example. Consider an application where we have servers in different availability zones that are communicating with users and logging their server events to a Kafka broker. And our goal is to implement a region monitoring system that identifies whether servers are experiencing errors and if so, sends an alert. Our log events have the following structure. They have a timestamp and then a separator to separate the timestamp from the event data. Then they have an event type, and if it's an error event, it has a code and a severity. Then they have the zone and the server that sent the event, and then a compressed message to describe the event. So we can formulate this application as a data flow graph where we first read events from a Kafka source, extract and parse error events, filter for error code 500, which is internal server error, group by zone over a time window, aggregate the average severity in this window, then filter for high average severity, and if it's high, we write an alert to a Kafka sink. We can implement this in Flink SQL by first defining our input table of raw events, where each event has a timestamp, a line containing the event data, and a watermark that lets Flink handle late arriving events. And then we specify how to ingest this data. For our output alerts, each alert has a zone, an average severity, and a window start and end that marks the range for which this alert is valid. So then we can extract error events by filtering for the error event type and then extracting the fields of the error event. Finally, we can create our output alerts by filtering for error code 500, creating a time window, grouping by the window start, end, and zone, where the average severity is greater than 2, and then selecting the fields of the alert into our sink. So now that this application is finished, assume that we maybe want to isolate the code that we have here for parsing so that we can reuse it for another application and also test it against the servers that are generating these events. To do this, we can use Flink's Java API and extract the code into a user-defined table function that contains the logic for parsing. And then we need to declare the input and output types of this function. And then we can import the function to SQL and use it in our query. So now that we are done, are there any problems with how we have implemented this application? One problem is that the SQL code is compiled separately from the Java code, and this means, for example, that we cannot easily push down predicates from SQL into the Java UDFs, since these UDFs are already compiled. Another problem is that the UDF is materializing fields that we never end up using in the query, and we cannot push down a projection to remove these fields early. Another problem is that we need to convert between SQL types and Java types, and this can be both cumbersome and also a potential source of errors, such as mixing up the order of fields. Another problem is that UDFs can execute arbitrary code that could potentially violate the semantics of the query language and leak sensitive data, and there is no easy way for the query language to verify against this. Finally, because we have implemented this UDF in Flink's Java API, we cannot easily port it to work on other systems and architectures, such as Apache Spark or non-JVM based systems like Rising Wave or Nebula Stream. So, are there any other options we can use to implement our application? Well, we could try to use Flink's DataStream API, and this API provides with higher order functions for processing data streams, and these take UDFs as arguments. So now that we've written all of our code in one language, at least it should hopefully type check. But if you run this program, you get a runtime error like this. This error says basically that the return type of this function could not be determined because its generic type parameters were erased. To fix this, we need to call the returns function and specify the return type manually. While this problem and many others like it are easy to solve, they only distract us from our real problem since they have no true relevance to our application. So, while the expectation is that data flow systems should be able to abstract the complexity of data flow execution, the reality is that, as a user, you still need to deal with a lot of complexity as soon as you start using user-defined functions, such as manually optimizing your code, making sure that the types are matching, and that there is no undefined behavior. So, how could we try and solve this problem? Well, one approach could be to try and extend Flink SQL with support for user-defined functions. But what if we were to just create a new language that solves all of these problems? What we propose is a new programming language named AquaLang that bridges the gap between streaming query languages and general-purpose programming languages. So, to explain AquaLang, we can revisit our example from earlier. An AquaLang program is a sequence of statements. These statements define user-defined types, raw events and error events, and then we can define also a parse function for parsing raw events into error events. Then we can define a query for our application just as you would in any other data flow library. However, unlike data flow libraries, AquaLang verifies that UDFs used inside of queries are side effect free and thus introduce no undefined behavior. AquaLang is also not closely coupled to any specific system, which means that we can compile queries to run on different systems. In addition to the functional syntax that AquaLang offers, we also support a relational syntax that is semantically equivalent to the functional one. So you can read this program like this. For each event in our source, we want to parse the event and iterate over the result, then filter by error code 500, group by zone, over a sliding window, and compute the average severity of errors. And then, if the average severity is greater than 2, we create an alert with these fields and send it to a sink. So while this relational syntax enables you to write programs declaratively as if you're writing queries in SQL, it also enables some optimizations. So in AquaLang, we optimize programs with a technique known as equality saturation. And what this means is that we have our initial program, which contains a query, the UDFs and UDTs mentioned by the query, and then we want to optimize this to a new program. We begin by converting this initial program into an E-graph, which is a data structure that efficiently represents a set of equivalent programs. And then we iteratively apply rewrites to this data structure to find more equivalent programs. And when we've reached a fixed point or a timeout, we select the lowest cost program, which is our optimized program. Now, I'll show how the AquaLang optimizer could rewrite this program. First, it could choose to inline the parse function into the query, and then remove the parse function since it's no longer needed. Then it can move statements from the inline function into the query. So here, each val adds a new relation attribute to the query. Then this if expression can be rewritten into a where clause since the else branch does not contain any logic. Then the rest of the statements can also be moved into the query. And now, since this from clause is only iterating over a single value, it can be rewritten into a select clause. Then this error event struct can be inlined into the query so that its fields become relation attributes. Since some of these attributes are unused, they can be removed completely. Then this predicate can be pushed down, which also means that the error code is no longer needed and can be removed from the select clause. Since these attributes are only used once, they can be inlined. Finally, the optimizer can rewrite these where clauses into a single where clause with a conjunction. And this is our final, most simplified query. Alright, so what more features does AquaLang have to offer? Suppose that we want to reuse this query for another application, but we would also like to make some slight changes to it, like handling other error codes. To achieve this, we can put this query inside of a function that parameterizes the input stream and error code of the query. Then we can call this function and use its result as the input to another query. By treating queries as normal expressions that can be put inside of functions, it's possible to write very compositional applications. AquaLang comes with a compiler that is able to generate code for different data flow libraries and host languages. And in this way, we achieve a strict separation between the programs that users write and the decisions related to how these programs should be executed. Currently, our main target is a Rust-based streaming runtime library, and we have initial support for running programs on Apache Flink. To conclude, AquaLang is a programming language that targets streaming data flow systems. It is designed to be compositional, safe, fast, and easy to use. We're aiming to release a beta version of the language later this year, and if you find the language interesting, please get in touch. Also, if you would like to learn more, we have a website, a GitHub, and a DEBS paper. Thank you for listening to this presentation.